Hello everyone. The first topic in this lecture is called as power of a lens. To define it, power of lens is defined as tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical center. So, if we look at a case of a convex lens or a concave lens, then these lenses will have different powers to deviate the light rays. For example, think of a case where a light ray is falling like this. Now we know that in case of a lens, the light ray would refract. So based on the lens, some lens may deviate, maybe like this, some like this, or some like this also. So based on the lens power, there will be different deviations. So we'll take any one light ray. The light ray should have gone like this, but because of refraction, the light ray is being refracted, and this would be the angle of deviation. So power of lens is defined as tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical center, which means when the distance of the light from optical center is say 1 meter, when this is 1 meter, in that case power of the lens is defined as tangent of the angle of deviation. That is called as power of a lens. Let's find out what is power mathematically. As seen here, we have taken a convex lens and let this be its principal axis. Suppose, let's assume that a light ray is falling on this lens at a given distance like this. Let's assume that the distance here is 1 meter. So this light ray, instead of going straight like this, it has been deviated by some amount. So here, if we draw a line passing through optic center, let's assume that light refracts at this point. So this light ray would deviate and it will be converged to a point like this. So this is the point where image is formed, and this would be its focus also. Now here this angle would be delta. As seen here, these two lines are parallel lines, and this is the transversal, which means even here this angle would be delta. Distance between C to F would be the focal length small f. In this diagram, if we find tangent of delta, and that would be given by opposite side, which in this case is 1, because by definition power is defined as a case where the light falls at a height of 1 meter by f, because the adjacent side is f. But by definition this would be power. So therefore power is equal to 1 by f. For a general case, if the height is h, then tan delta will be given as h by f. This is for general case, but if h is equal to 1 meter, this is what we get. That is called as power. As seen here, since it is a converging lens, for a converging lens power is positive. So whenever power is positive, it means the light rays are converged. Whenever power is negative, it means the light rays are diverged. So keep this in mind also. And we have been seeing in the numericals that in many cases the focal length is in terms of centimeter, but to define power from this form, F should be in meter. So power is given as 1 by F if F is in meter, and the unit of power is called as diopter, which is capital D. Suppose if the focal length is in centimeter, then in that case we multiply by 100 by F, that becomes the power. Let's recap whatever we learned till now. That is, let's compare the equations for a mirror and a lens. We look at a mirror and then a lens. The first formula what we learned in case of mirror was F is equal to R by 2. For a lens, the form is given by 1 by F is equal to N for lens by N for surrounding minus 1 into 1 by R1 minus 1 by R2. The second form what we studied was the mirror equation, which read 1 by V plus 1 by U is equal to 1 by F. In case of a lens, it is called as lens equation or lens formula, which is 1 by V minus 1 by U is equal to 1 by F. The third thing what we learned was magnification, which was defined as height of image by height of object, and this was equal to minus V by U. Even here, the magnification is defined as height of image by height of object, and that was equal to V by U. Observe the change in signs. It's plus here, it is minus here, it is minus, it is plus here. Observe these things because, as I've been telling, the numericals are quite straightforward in case of optics, but be sure with sign conventions. The power was minus 1 by F and the power here is plus 1 by F, but in both the cases, if power is positive, it means light rays are converged, and if power is negative, that would mean that the light rays have been diverged. The next topic is to find effective focal length. There can be instances where we need some focal length, or we can combine few lenses. We cannot make a length of all possible focal lengths. So suppose if you want some value, in that case we can combine the lenses. For example, imagine that we want 15 rupees. So we can't print a note or make a coin of 15 rupees. So what we can do in that case is we can take 3 coins of 5 rupees, or we can take one 10 rupees note and a 5 rupees coin. So the basic purpose of adding money is to obtain a desired amount. The same way, in case of lens, we can obtain a given focal length by combining them. Keep in mind that the lenses will not add up as it is adding up here. For lenses, we have a different formula, or the effective focal length has a different form to it, but the idea here is the lenses are combined to obtain a desired focal length. Again here, the derivation could be used for any two combinations. That is, we can take off two convex lenses or two concave lenses, or we can have one concave and one convex. The formula will still hold good, but for derivation purpose, we will assume two convex lenses. That's the first point. And here we are doing only for two thin lenses, and also here will derive when the lenses are in contact. So the formula what has been derived here, or what will be derived here, is a case when the two lenses are touching each other and these are thin lenses. So let's begin. Let's draw two lenses. We call them as lens 1 with focal length f1, and then one more lens will be touching this lens only, such that for this lens the focal length is f2. Let us draw the principal axis passing through the two center of curvatures. Now here we saw that in case of lenses, the reference point was the optical center. Since we have two lenses here, we will have two optical centers. We'll call it as C1 and then C2. But for the entire system, for these two lenses, C1 or C2 cannot be the reference point. So we need a common reference point, and that common reference point is taken as the point where the lenses would touch each other. We'll call this point as, say, C. So the point where the lenses are in contact is the reference point in this combination. Now what will happen is, suppose somewhere here an object is placed, say at point O. A ray of light from this object will fall on the lens like this. We saw in the previous classes that this light ray would refract, and this light ray was tending to move towards a point. It was trying to move towards a point like this, but because of presence of lens 2 with focal length f2, the light ray doesn't go to the point I dash. So I dash is the point where the image would have been formed if we had only one lens. But because of presence of one more lens, the light here is again refracted at the second lens. Therefore, the image is formed not at I dash but somewhere before I dash, and we call this point as point I. So for the entire system, for the two lenses, O is the object and I is the image. I dash would have been the image if the lens f2 was not there. Now what we do here is, we need to find an equivalent lens, which means we take a case where we replace these two by a single lens called as equivalent lens, for which the focal length would be f equivalent. Equivalent lens here means that this lens would form the image at the same point as these two lenses are forming. That means that, just imagine a case where we have an object here and somewhere we have a screen like this. Object and screen are fixed. So whether we place these two lenses or the single lens like this, the distance of object and image will not change, which means light doesn't know whether there is two lenses or one lens. That is called as effective lens. Effective lens basically means that single lens which produces the effect of the two lenses kept earlier. Now let its focal length be f suffix e. Now we'll start the derivation. Now for the combination CO would be minus u by sign convention, because light is moving from left to right and we are moving from right to left. And then Ci would be plus v. With that in mind, we will start the derivation. We'll take the lenses one by one. So first, consider lens L1. So let the first lens be called as L1 and second lens be called L2. For lens L1, we'll redraw the lens like this, and then somewhere here optical center we have the principal axis. At this point O, an object is kept. Light falls on this lens, light refracts, and the image would be formed at the point I dash. Keep in mind that the image would be formed at the point I dash. So in this case, this is the image point. Let C1 be its optical center. If we use the lens equation for this lens, we know that 1 by f is equal to 1 by v minus 1 by u. So if we use the lens equation here, then what we get would be 1 by f1 is equal to, for this lens, v would be 1 by c1 I dash, because for this lens u would be minus c1 into o and v is equal to c1 into I dash. So minus of 1 by minus c1 into o, that is 1 by f1 is equal to 1 by c1 I dash plus 1 by c1 into o. We will call this as 1. Similarly, we'll draw it sidewise only. We will consider lens L2. For lens L2, what we find is, we find that the light ray, this light ray was trying to go towards the point I dash, but because of one more refraction at the lens L2, the light ray would deviate and finally the image is formed at the point I. For this lens L2, C2 would be its center of curvature. In this case, I is the image. Now the question is, for the lens, where is the object? The object cannot be at O because O is the object for lens L1. So for lens L2, the image formed because of the first lens, which is I dash, this acts like a virtual object, because of which the image is formed at the point I. In this case, U is equal to C2 into I dash and V is C2 into I. If we use the lens equation here, then 1 by F2 is equal to 1 by C2 into I minus 1 by C2 into I dash. That's called as 2. Remember, we're deriving the equations for two thin lenses which are in contact. So for thin lenses, it means that the point C1 is somewhere here, the point C2 somewhere here. For thin lenses, the points C1 and C2 would be close to each other. So for thin lenses, we can replace the points C1 and C2 with C, because C is our reference point. So replacing points C1 and C2, why? Because these are thin lenses, and then adding 1 and then 2, then what we get would be, the left hand side would be 1 by f1 plus 1 by f2, that is equal to 1 by ci dash, because we are replacing the points C1 and C2 with C, 1 by CO plus 1 by Ci minus 1 by C into I dash from here. this term and this gets cancelled. Recall what was CO. CO was minus U. So what we get here is 1 by F1 plus 1 by F2 is equal to, it is minus 1 by U plus 1 by V, because Ci is plus V. Therefore, this is equal to 1 by V minus 1 by U, where 1 by V would be this term and this will be 1 by U with a minus sign. We'll call this as 3. Now, what is the expression for an equivalent lens? That is, for this equivalent lens, what is the lens equation? Here, 1 by Fe is equal to, this is C, so it will be 1 by V minus 1 by U. We know this for this is lens equation. We call it as 4. So, comparing 3 and 4, it is very obvious that the right hand sides are equal. So, therefore, what we get would be 1 by F equivalent is equal to 1 by F1 plus 1 by F2. So, this is the required expression for the effective focal length. As I told you earlier, the focal lengths don't add up directly, rather they go inversely, they go by reciprocal. That is, the reciprocal of the equivalent focal length is equal to sum of reciprocal of individual focal lengths. Keep in mind that even though this equation was derived for two convex lenses, this formula holds for any two combinations. And while using this equation or this formula, always use sign conventions, which means if we take off one convex lens and one more concave lens attached together, and if this focal length is say 10 centimeter, this 12 centimeter, in that case F1 would be in this numerical plus 10 centimeter and F2 would be minus 12 centimeter. So always use this with sign convention. Now one question which comes to mind is, why do we need to use so many sign conventions? We are already using the sign convention once here, and we are using it once more here because we took CO as minus U. That is because if you don't use sign convention earlier, then we may get different equations for different positions of the object. So whether it is in this case or in case of lens equations or lens maker's formula, we use sign convention twice so that we need to remove the effect of this convention. To remove the effect of this sign convention, we use it once more as given here. Otherwise, we would get different formulas for different equations. So in terms of power, we can say power of equivalent lens is equal to P1 plus P2. So keep in mind that this is for two lenses which are touching each other. Now we'll take a general case where we have two lenses with focal lengths F1 and F2, but in this case the lenses are not touching each other, rather they have a separation between them that we call as D. So D is the separation between the two lenses. So in this case, the effective focal length, or 1 by F, here we call as F only. So this effective focal length is 1 by F1 plus 1 by F2 minus D by F1 into F2. It's not been proved here because the proof of this is beyond the scope of class 12 syllabus. This can be proved using something called as matrix method in optics. It is not there in this course. So for now, just take this to be true because there could be numericals based on this formula. Again, if the lenses are touching each other, in that case D becomes 0. If D becomes 0, this is what we're left with. So whatever we derived in the previous slide, that comes from here only. In terms of power, we get power equivalent is equal to P1 because it is P1 for this one, P2 because we have derived that power is equal to 1 by focal length minus P1, P2 into D. Now think of a case where we have many focal lengths or many lenses touching each other. In that case, the effective focal length would be the sum of reciprocal of each focal length is what we get. In terms of power, P is equal to P1 plus P2 etc. Keep in mind that power adds up. Now magnification doesn't add up. That is, if you look at n lenses which have different magnifications, then in that case the magnifications would multiply. This is very, very important. So it becomes m1 into m2 etc. If you have more than 2, just keep multiplying them. So the magnification multiplies. This is very important because this is the principle of compound microscope. We will see it in later lectures, but for now understand this point. We will take one example to understand the earlier concepts. Example says a lens has a power of 5 diopters in air. So when a lens is kept in air, its power is 5 diopter. What will be its power if it is completely immersed in water? Do remember that the focal length of a lens would change based on the surrounding medium also. So question says what will be its power if it is completely immersed in water, given refractive index of glass is 3 by 2 and refractive index of water is 4 by 3. So let's recall the equation which connects power with the surrounding refractive indices, and that would be the lens maker's formula, which says 1 by F is equal to N for lens by N for surrounding minus 1 into 1 by R1 minus 1 by R2. Recall that for convex lens, because the power is plus 5. Plus 5 means it means that the focal length is positive, and you have seen that focal length is positive for a convex lens. So for a convex lens, this is modified now, and what we get would be 1 by F is equal to NL by NS minus 1 into 1 by R1 plus 1 by R2, because for convex lens R1 is positive and R2 is negative. This is what we get. In terms of power, 1 by F is called as power. So we can write this as just power only. Now since the question says it is kept in air, then power in air would be N by N for lens minus 1, because N for surrounding is 1 in the first instance, 1 by R1 plus 1 by R2, and N for lens is given as 3 by 2. So you can write this as 3 by 2 minus 1. This is for power in air, and even this is given as 5 diopter. So from here 5 is equal to half, because 3 by 2 minus 1 is half, into 1 by R1 plus 1 by R2. Now if you look at the second case, question says what will be its power if it is completely immersed in water. Use same form, then what we get is, we get power in water. I just write P in water, that is equal to N for lens, which is 3 by 2, and N for surrounding would be 4 by 3, because 1.33 is 4 by 3. So it is 4 by 3 minus 1 into 1 by R1 plus 1 by R2. If we divide these two equations, divide this and this, and from here this term gets cancelled. In such numericals, it is easy to divide the terms than substituting. Therefore, what we get here is 5 by power in water is equal to, it is half by this term here, it is 3 by 2 by 4 by 3, and 3 goes on top, it becomes 9 by 8. So it is 9 by 8 minus 1, that will be 1 by 8. 8 goes on top is equal to 8 by 2 because 8 goes on top. So from here 2 1s are 2 4s are. Therefore what we get would be, if you bring this 4 down and take power for water side, then 5 by 4 would be power for water, or power for water or power in water would be 1.25 diopter. So this is the required answer. Thank you.